One of the first types of circuits we're going to look at is a circuit called a series circuit, or a circuit in which all of the elements, the resistors, etc., are wired in what we call series. So we have to think for a second, what does the term series mean? Well, it means very much what it means in things like books and movies and TV shows. It basically means one right after the other. So a book series, a movie series, a television series, you generally should watch them in the right order. So in a circuit, it means the exact same thing. Elements are wired one right after the other. So you have to pass through the first to get to the second, pass through the first and second to get to the third. There's only one pathway for electrons. That's what a series circuit means. You must go through each individual element in order. You have no other options. So if you're an electron, like we said, you have to go through, in this case, resistors 1, 2, and 3. I like to represent circuits with what I call the Tollbooth analogy. So imagine we have three different roadways, and to get from point A to B, we want to collect a $6 toll. So anytime a car passes down this roadway from A to B, we'd like to make $6. Well, we have a few things we could do here. We could place one toll booth and charge $6. So that means we're going to have some cars approaching, they pay the $6, and then they leave. Well, if we think about those cars, the drivers will have $6 in their wallet. I mean, we'll assume that. They have $6 in their wallet as they approach the toll booth. They will spend the $6, and then they will have no money left as they get to their destination. This is, of course, assuming they only began with $6. We could also add two toll booths and charge $3 a piece. Well, cars would come through, they'd pay the first toll, they'd pay the second toll. The money would be a little bit different. They'd have $6 in their wallet as they approached the first toll booth. They would have $3 in their wallet as they approached the second, having spent 3 at the first. And they would end with 0 because they're now at their destination and they paid the entire toll. You might see where this is going, but now we could also have 3 toll booths, and each toll booth only charges $2 a piece. All right, the cars are going to go ahead. They're going to start to go through. They start with $6 as they approach the first, 4 as they approach the second, 2 as they approach the third, and then they get to their destination with 0. We recognize that in all 3 cases, they spent $6. They went from the same point A to the same point B, and they were charged the same amount. But obviously, in the real world, one of these would probably be the worst option in terms of the amount of traffic that it's going to cause. But we'll take a look at that in a second. The same goes for a series circuit. If instead of considering tolls, we consider a voltage, we can assume that if you're going to go from the negative to the positive terminal of this circuit, well, if, again, we design it so that you have to spend 6 volts, you're going to have 6 volts leading up to that resistor. 6 volts is what the drop in voltage will be as you go through, much like paying a $6 toll, and you'll have 0 volts on the other side of this. So electrons will flow from a higher voltage, 6 volts, to a lower voltage of 0, spending their energy as they go through that resistor. Likewise, in the second case, if you have 2 resistors, well, you're still going from the same negative terminal to the same positive terminal, so you still have to spend your 6 volts, so to say, but now it's going to be spent a little bit differently because you have to make sure you can get through 2 resistors. Likewise, we could have 3 resistors, and the same analogy applies. We're still spending 6 volts, but we're spending it across more resistors, so we spend a little bit less at each. 2 volts as opposed to 3 or 6. Now, much like in that toll booth example, if we are going to collect 6 volts or $6 in my analogy, we would never want to throw 3 toll booths together because that is going to slow everything down. Imagine if you were approaching a toll booth, and instead of just charging everyone $6, you had to pay 2, drive forward about 50 feet, pay another 2, drive forward another 50 feet, pay another 2. The state is still getting their $6, but oh my gosh, the current is going to be so slow because the traffic is going to be so high. There's too much resistance there. So just understand that in a series circuit, which is a circuit that has one pathway, as you add resistors in series, you increase the resistance because every electron has to go through every resistor. Every time you add a resistor, you're adding more stuff, another obstacle, because there's no pathway or no option around it. So one of the big major concepts about series circuits is adding resistors in series is going to increase your resistance and decrease your current. Another important thing to notice is because there is only one pathway, all the resistors experience the same amount of current. Just like if you had 3 separate toll booths charging $2 a piece and there was only that one route, each toll booth will experience the same number of cars because there's nowhere else for them to go. Yes, you're going to slow down the rate at which those cars move through. You're going to decrease the current, but you are still going to see every car at every one of those booths. Last but not least, the voltage splits among the resistors. So likewise, when you have one toll booth, you can pay all 6. When you have 2 toll booths, we're required to pay 3 and 3. And when there's 3 toll booths, we're required to pay 2, 2, and 2. So the voltage is what splits among resistors in series because you have to ensure you have the energy to get through each. But the current is the same because every resistor, since there's only one pathway, is going to see the same number of electrons over the same amount of time. I'm going to show you how to use and apply these in a more mathematical approach in the following examples, and we'll go forward from there.